Hello everyone, my name is Daniel Wynn, and in this video I'll be going over Nanoelectromechanical Systems devices, also known as NEMS devices, brought to you by work done in the University of Florida's SCAN Lab, under the supervision of Aslam Khan, Litin Kumar Biswas, and Dr. Naveed Asadi. The content of today's video will go into detail about Nanoelectromechanical Systems devices, aka NEMS, and will be outlined by a quick overview of their predecessors, Microelectromechanical Systems devices, also known as MEMS, followed by an overview of NEMS themselves, then the industry, the market, and the value chain revolving around NEMS, moving on to specific types of NEMS switches, moreover with more NEMS switches and their applications, fabrication of NEMS, packaging materials and processes of NEMS, hardware vulnerabilities, and how NEMS can be used as a security mechanism for these vulnerabilities. And then the video will close off with the glossary for abbreviations and acronyms discussed throughout this presentation. Before diving into NEMS technology, I will be going over a brief overview of MEMS technology. MEMS stands for Microelectromechanical Systems. They are devices that operate on a microscopic scale, between 20 and 1000 microns, and integrate mechanical and electronic components on the same silicon substrate. MEMS technology are used within a wide range of applications, such as sensors, actuators, and microphones. Shown in both images are MEMS-based actuators, with the left being a surface micro-machined resonator and the right being a micromotor. MEMS technology requires sophisticated manufacturing techniques such as photolithography and etching, enabling production of these high precision and scalable devices. And with this, MEMS technology is currently being widely used in a variety of fields. Moving forward onto a brief overview of NEMS technology. It is very similar to MEMS technology. The biggest difference is that NEMS stands for Nanoelectromechanical Systems, due to NEMS technology operating on a nanoscopic scale rather than a microscopic scale. This makes NEMS technology operate on a smaller scale than MEMS technology by an order of 3 magnitudes. NEMS technology is still being developed, but they have a wide range of potential applications, ranging from nanosensors and nanoelectronics to nanomedicine. And because of their even smaller scale, fabrication of these devices requires specialized manufacturing techniques, such as electron beam lithography and nanoimprint lithography. The figures shown towards the right are an electron micrograph of NEMS objects fabricated in a single crystal silicon by utilizing electron beam lithography, and is then completed with surface micromachining. And with how widely used MEMS technology is currently being used, the potential of NEMS technology seems inevitable in many industries in the future. Focusing on the industries of NEMS devices. NEMS devices have the potential to be applied in the following industries: electronics, biomedical, energy, aerospace, and defense industries. In the electronics industries, companies such as Agilent Technologies have entered the NEMS market through advanced development of NEMS devices and technology. While within the biomedical industry, the uses for NEMS devices are drug delivery systems and disease detection sensors. And Volcano, a current competitor in the biomedical space, are currently utilizing MEMS devices and are sure to take full advantage of NEMS devices once they become more developed. In the energy industry, companies such as Envision can use future NEMS technology for energy production and storage applications. In the aerospace industry, Boeing has the potential to upgrade their use of MEMS-based sensors and actuators for enhancing aerospace systems to NEMS-based sensors and actuators. And lastly, BAE Systems and other companies within the defense space also have similar use for future NEMS devices as sensors and actuators for enhancing their current defense systems. Currently, in the global nanoelectromechanical systems market share, the figure displays key regions occupying the market share: North America, Europe, Asia Pacific, and the rest of the world. The main drivers of the NEMS market are technological advancements in nanoscale components and nanomaterials and increasing investments. And while with that, the main restraints holding back NEMS are the high prices of nanomaterials and the processing and fabrication of the NEMS devices themselves. Furthermore, the value chain of NEMS technology follows the value chain of MEMS technology, beginning with the front end of side of things. It begins with a market analysis and product definition through the examination of the needs of the market while taking into account the competitive landscape and the competency of the market. With this in mind, the product can be developed with the solution in mind, with the solution for the part of the market. And in this case, NEMS technology has a deep market with a plan of minimizing size while increasing efficiency of these electronic and mechanical systems. After this, design of the device and package are then conceptualized and analyzed. Then, the process design flow is used to begin manufacturing production in the wafer foundry with fabrication and is then finished off in the back end of things with package or assembly of the NEMS devices and testing. Once the back end is complete and the NEMS device seems to be more than adequate to be brought to the market, the product can then be shipped to the market. One of the main applications for NEMS-based devices are NEMS switches. They can control the flow of electricity at the nanoscale level by taking advantage of the properties of silicon. They work by using mechanical movements and electrical signals to open or close an electrical connection, just like a light switch. Silicon-based NEMS switches offers highly attractive components for the development of new transducers. These miniature devices possess remarkable sensitivity, responsiveness, and precision, making them highly desirable for a wide range of applications across industries. One significant trend in silicon NEMS technology is the integration of movable silicon devices within CMOS platforms. By combining mechanical functionality with CMOS electronics, we can create powerful and highly integrated systems. This integration not only enhances performance, but also reduces power consumption and improves overall device reliability. In advancements, engineers have successfully engineered ultra-thin silicon nanowires and arrays into high-speed vibrating devices. These devices exhibit impressive characteristics such as high-frequency operation and low power consumption. The application potential for these devices is immense, from resonators to sensors to actuators, enabling the development of next-generation high-performance systems. Furthermore, suspended silicon nanowires and arrays serve as vital intermediates in the journey towards creating silicon NWGAA 3D nanofets. These suspended structures provide enhanced control over the electrical properties of the devices, leading to improved performance and scalability. The impact of these nanofets can be seen in advanced logic circuits and memory technologies, promising exciting possibilities for the future. Lastly, the fusion of technologies have played a significant role in the progress of silicon NEMS. State-of-the-art silicon-on-insulator technology has enabled the achievement of 8-inch wafer scale VLSI of silicon NW NEMS. This fusion together the benefits of SOI technology with the capabilities of silicon NEMS, facilitating large-scale production and commercialization of these devices. Silicon carbide NEMS technology has made remarkable strides, resulting in robust and reliable NEMS switches and logic building blocks. These devices showcase exceptional performance and durability across various applications. A noteworthy achievement of silicon carbide NEMS devices are their ability to achieve an astonishing number of switching cycles without failure. They have recorded over 10 to the 7th power to 10 to the 10th power switching cycles, demonstrating reliability and endurance at room temperature and high temperatures up to 500 degrees Celsius. These devices also exhibit resilience in ambient air, offering versatility for real-world applications. These devices offer a range of geometric configurations and signal readout schemes, allowing for adaptability to different system requirements. Their versatility enables seamless integration into various device architectures and signal processing schemes. Additionally, these devices excel in scalability and manufacturability, making them highly attractive for large-scale production. Moreover, silicon carbide NEMS technology enables the integration of hybrid NEMS transistor systems. This integration combines the unique capabilities of NEMS devices with the functionality of transistors, paving the way for advanced circuitry and system design. The hybrid integration enhances performance and increases functionality in a single device. Overall, silicon carbide NEMS technology has proven itself with its robustness, reliability, endurance, offering adaptability, scalability, and the potential for hybrid integration. These advances hold promise for the future of advanced electronics and signal processing applications. Nanoelectromechanical systems, NEMS switches, come in different types, each with unique characteristics. The following NEMS switch types are the ones that are currently being researched to be used for reconfigurable packaging. The curved cantilever switch is a thin, flexible beam that bends to control current flow and is typically made up of silicon, platinum, titanium, and gold. Platinum-coated silicon switches are made of silicon coated with platinum, enhancing the conductivity of it. Clamped beam switches use anchored aluminum beams to flex between on and off states. 65 nanometer copper switches are fabricated using advanced technology, with copper components for efficient signal transmission along the titanium nitride and tantalum nitride. Hammer-shaped switches resemble hammers and actuate between on and off states and are usually made with tungsten. These switches offer diverse features such as bending, material coatings, anchoring, and shape, resulting in variations in sensitivity, performance, and applications. Understanding these differences allows for tailored use in electronic systems and encourages exploration of their distinct capabilities. Moving on to the main fabrication methods for NEMS devices are bulk micromachining, surface machining, and LIGA, also known as lithography, galvanoforming, molding. Bulk micromachining is shown in the far left figure, where it begins in part A with a potassium hydroxide etch, followed by a deep boron diffusion in part B, then a shallow boron diffusion in part C. Part D showcases a silicon anodic bond to glass and ends off with the removal of the glass. Surface micromachining is shown in the middle figure, beginning with a sacrificial layer being deposited on top of the silicon substrate in part A. Following that, a structural layer is then added before the sacrificial layer is removed. For the LIGA fabrication process, it is shown in the far right figure. In the sacrificial LIGA process, part A begins with UV lithography for sacrificial layer patterning, moving on to X-ray lithography in part B, electroplating in part C, and finishing off the structure, releasing in part D, with part E showing a top view of the movable structure overall. Moreover, with other main methods of NEMS fabrication methods are wafer bonding, soft lithography, nanomachining, and nanolithography. The table shows that micro-contact printing and micromachining are the only current techniques for fabrication at the nanoscale for creating pattern SAMs. The figure on the right depicts a schematic diagram of the processing steps required for micro-contact printing, with views all shown from the side profile. The packaging materials and processes are critical for MEMS and/or NEMS device protection. Hermetic packaging, which is the outer packaging of the components that protects the components from environmental damage, typically uses metal, ceramic, glass, or silicon to prevent moisture and corrosion. Packaging of these devices can provide access to the environment, electrical fluid interconnects, and optically transparent windows. Packaging design has to be considered with device design and can account for 75 to 95% of overall cost of MEMS and NEMS production. As figure, the basics of NEMS packaging is reminiscent of MEMS packaging, with scaling taken into account. The main differences are the actual processing and manufacturing techniques required, and they are more high-end techniques to be able to fabricate at that scale. Moreover, some design considerations of NEMS packaging are thickness, wafer dicing, cooling, power dissipation, and mechanical stress isolation. Within the die attach process, individual dies are mounted into a package. Electrical interconnects are typical bonding and flip chip bonding, while the fluid interconnects are typically capillary tubes and self-aligning fluid ports. The figure below shows one of the design considerations, stress, in one of the electrical interconnects, wire bonding. There it can be seen that the stress is fairly balanced around the contact point. Other packaging techniques include benzocyclobutene, aka BCB, capping, and vacuum seal. The biggest difference between the two are that BCB capping is a coating, while vacuum seal has an enclosure, and BCB capping is usually a permanent process while vacuum seal is seen to be more flexible. Shown in the left figure, the process flow of BCB capping is as follows. First begins with an anti-adhesion layer coating in part A before BCB caps are formed in part B. Next, MMIC wafer bonding occurs to support the wafer in both parts C and D, which is then a support wafer is perforated in part E. In part F, PMMA sacrificial etching occurs, followed by BCB capped MMIC on the dicing tape, occurring in part G. The BCB capping is finished off with the dicing of MMIC. As for vacuum sealing, it is shown in the right here. It first begins with fusion bonding, followed by microcavity etching and RCA cleaning. After that, VHF etching occurs, which is a vent hole opening and structure release before the vent hole is then closed with hydrogen annealing. Moving forward is etching of the trench with hydrogen diffusion through the trench, and the entire process is then finished off with the etching of the membrane. One of the advantages to NEMS are that they can be a solution to hardware security vulnerabilities for integrated circuits. Some of these vulnerabilities are reverse engineering and hardware trojans. Reverse engineering can affect the hardware such as the chip itself or the PCB. Reverse engineering can leave room for counterfeit hardware to pop up, reduces reliability, and introduces more vulnerabilities into technology. Hardware trojans, on the other hand, can modify ICs directly and are inserted during the fabrication process. They can also reduce reliability of technology, changes functionality, or even leak information. As stated previously, NEMS can be a solution to these hardware security vulnerabilities, as they are a security mechanism. NEMS-based devices can be advantageous in reconfigurable packaging and smart interposers. With reconfigurable packaging, it utilizes NEMS-based sensors for real-time monitoring of the device, so when a hostile entity is detected, the packaging can then be rearranged at any time remotely to combat or hinder the entity. This is also very customizable, allowing for the packaging to be changed to target specific vulnerabilities based on what the NEMS sensor detects and monitors, while also keeping it very easy to integrate the NEMS component within the entire device itself. As a smart interposer, NEMS technologies make use of NEMS sensors monitoring capabilities, detecting whether tampering is occurring, and can monitor things such as voltage and current. Whenever abnormalities occur, the NEMS device can be used to shut off the device remotely if compromised to prevent any leak of information or for overall protection in general. Here's the glossary for some of the abbreviations and acronyms seen throughout the presentation. And here are the references.